So let's recap what we learned last week. Not last week, but last time. Last time we covered the performance analysis of communication systems, right? Typically, when we talk about communication systems, we typically look at the MIMO systems, right? We extend the general conventional performance analysis to the MIMO setup so that we want to see what happened in the MIMO. And in order to do the performance analysis, first thing to do is that we have to define the performance metric, right? And the popular performance metrics are error rate. It could be bit error rate or symbol error rate, and the capacity. These two are the performance metrics. Typically, the error rate, you want to minimize it, you want to reduce. But capacity is when you want to increase it or maximize. Okay? This picture, you already know this, right? This picture basically shows you that, this MIMO, in fact, can be illustrated or, can be considered as a water pipe. This case, in this technique, we're going to use a diversity technique for these two, 2x2 MIMO. So you have one single water pipe, but this water pipe is thicker than normal because we have a diversity order of not 1. In this case, you can have even diversity order 4. So this is very thick, right? Which basically means that our error is pretty less. Whereas when you use this 2x2 MIMO system, you can also run this one as a special multiplexing. In that case, you have two independent pipes. Each one is a normal diversity order 1. So you have some pretty, compared to this one, it has a pretty large amount of errors, but we have a two independent stream. So therefore, you can increase the capacity. Whenever we look at the performance analysis, we have to look at very carefully about the channel, because the channel is the one that basically try to reduce your performance. So the performance analysis always depend on the channel. Typically, the Rayleigh channel is used for performance analysis because this is the one that we always use to model the channel. This is the PDF of Rayleigh fading amplitude, and this is the SNR. The performance analysis always depend on the SNR, not the amplitude. Therefore, when we do the performance analysis, we always use this one. But this one, as you know, is not exactly a Rayleigh distribution, mathematically speaking. This one is an exponential distribution. And now you understand why we use exponential distribution for Rayleigh channel, right? Because this is a SNR, meaning that this is a power distribution, right? So we are always using this distribution. And also, sometimes it is very useful tool to use MGF, okay, moment generation function. This is a very useful tool. Therefore, we also want to know the MGF of the Rayleigh channel, which looks like this. And how to get this is actually a Laplace transform. And after you do the Laplace transform of this one, you take S, you take the minus S instead of S. Okay, simply speaking, that's what you get. There are other channels. For example, Rayleigh channels, there are also other channels. But another channel that is also popular, not as popular as Rayleigh, but some popular is Nakagami channel. And the reason that Nakagami channel is also popular by a scientist is that this is more general channel. We say that Nakagami channel is general channel. The reason is that, as you see here in the PDF of SNR, this Nakagami channel has two different parameters. Earlier in the Rayleigh channel, it is defined only by one parameter, which is the average SNR. But in Nakagami, we have one more parameter called M. This M is called the fading parameter. So by changing this M, you can make this Nakagami channel to be Rayleigh, if you like. So Rayleigh is going to be a special case of this Nakagami. Or this Nakagami can be, if that M equal to half, 1/2, this one goes to Gaussian. Or sometimes this one goes to some other channel,
which doesn't have a name, but by changing this M, you can convert this one into several other channels. That's why we call this one as a general channel, and it is interesting to find out the performance analysis of the system based on this channel. Okay, and the nice thing about this one also is that this fading, this PDF is a function of exponential and the polynomial. Okay, this is just multiplication of these two, which is preferable because whenever we do performance analysis, right, we're going to bring this one and put it inside the integral equation. Always we have to solve the integral equation. Okay, so from that point, we want to have exponential function and the polynomial. That way it's easier to solve the integral equation, right? If you think about the Raysian distribution, okay, Raysian distribution has a some other function like Bessel function here. In that case, even though Raysian distribution is actually useful and it even has a physical meaning, it's a little bit hard to deal with because you have a Bessel function here and put that inside the integral, it's difficult to solve. Okay, so that's why this is popular. This is easy to handle in performance analysis. Okay, another performance metric is capacity. And typically capacity, we first start with the Shannon capacity. In AWN channel, the Shannon capacity is defined by log 2, 1 plus SNR, right? And this is SNR. P is the power, transmit power, and this is noise power, noise variance. Okay, that's the case of AWGN. But whenever we have a fading channel, now we have H, right? In that case, this is the transmit power which goes through the H, the fading. So this H is square, since H is a fading channel amplitude, right? We have to consider the square, which is going to be kind of channel power or channel gain, right? You multiply the channel gain into the transmit power, then this is going to be receive power. Divide by N naught, that's going to be your receive SNR. So somehow here, this log function, right? This is the capacity when you received this one, okay? From the receiver perspective, this is the capacity. And what we want to know is that, this P of gamma, which is the SNR distribution, and you do an integration. That's going to be the capacity at the receiver, okay? This case and this case, as you see here, the difference is that in this case, right, the CSI, the channel state information is only available at the receiver. And this case is where the channel state information is also available at the transmitter. These two make a big difference. The reason is that some of these we're going to cover today, but as you can see here, the difference comes from the P. In this case, P is a constant because P is a transmit power. Transmitter has no idea about CSI. So it just transmits the same power all the time. But in this case, right, the transmitter knows how the H changes. Okay? So considering that, what transmitter can do is that transmitter can also vary its own power, its own transmit power. Okay? We're going to cover that in a minute. Okay? If you do that, then generally you can expect a higher performance, higher capacity. Okay? Okay, these are the BR analysis. We've covered this one many times, so let me just quickly cover that, and maybe you can skip this. Q function is popular for performance analysis because we are always dealing with the Gaussian distribution. Noise is a Gaussian distribution. And when you deal with the Q function, again, when we do the analysis, this Q function also needs to be inside of your integral equation. Okay, so considering that, now the Q function actually is a integration function. Okay, we just simply, this one cannot be simplified further. So this is simply written as a Q function, right? And what we need to do is that we want to analyze the performance over a certain distribution. So what you need to do is say this one has to go inside, like this one, right? Inside of, not this one, but like this one. So Q function has to go inside the integral equation, and this one is the PDF, for example, Rayleigh, right? So this Q function is inside of this integral equation. Now, we don't know probably how to solve this, okay? This is not exponential, this is not polynomial, so maybe high school, calculus is not enough to solve this integral equation. That's why sometimes it's useful to replace the Q function into another form. Even though Q function, in this alternative representation, right, Q function is replaced to another integral equation. So in that case, you put this one in here, right? Then it's going to be a double integration. Although it looks difficult, in fact, that's even easier, okay? That's why we try to use Q function, alternative Q function. That's sometimes very useful, okay? That's what I'm trying to introduce you. Especially for performance analysis, that's one technique you can use. Another way to do it, another popular way for performance analysis is sometimes to use the MGF, moment generation function. And here's a definition of moment generation function. As you can see here, this one is very close to Laplace transform, except you use S instead of minus S. Okay, that's what you see here. For Rayleigh and Nakagami, you can find the MGF for each of them. Okay. So using those things, right? As I mentioned earlier, in this case, in this example, by the way, this example is to find the bit error rate for any modulation. You see that there's alpha here, there's a beta here. These alpha, beta are constants that depend on your modulation. If you use bit error, if you use a BPSK, generally this is 2, this is 1, right? If you use another modulation, higher order modulation, you can find its own alpha and beta. Although this is a very close approximation, this approximation actually pretty close, pretty tight into the actual BER. So it's very popular to use this one. Okay, so this is a kind of general bit error rate, approximation bit error rate of any modulation. And then you use your own fading profile, Rayleigh or whatever, right? So in that sense, this equation, this integral equation is a generic performance analysis equation, okay? And replace the Q function into integral equation using alternative Q function. Then you switch these two integrals, right? And eventually you can replace this one into MGF, like this one, right? And then after that, once you decide your own fading, let's say Rayleigh, then in the previous slide we already talked about the MGF of Rayleigh. So you can simply replace that into your own MGF, for example, Rayleigh, right? And after that, you try to solve this one, but eventually you get this integral equation, okay? Integral 0 to phi over 2, and some sine square divided by some sine square plus some other constant. This is kind of pattern that you want to find out. Sometimes there is this term to the power something, okay? For example, like this, right? Sometimes you have this one. So there are certain pattern, okay? You are not trying to solve this one. This is the end of your performance analysis. Whenever you find this kind of pattern, there are several other patterns. For example, right? There may be inside of integral, there may be 2 of these terms. Maybe one of these terms multiplied by something like this. Okay? There may be 2 of them. That's another pattern. There are several patterns. Whenever you find that kind of pattern, okay, then what you need to do is that you have to refer to one of our books. Okay? There are some books that already solve this mathematically and give you a closed form solution. Okay? If you are interested, then maybe you can use Mathematica or some other the computer tools to solve this one. But in fact, you don't have to. Whenever you get this one, in order to get this one, you have to do all these things, right? You have to solve it by your hand. But whenever you reach these things, then you just refer to the book. That book will tell you what would be the closed form. Okay? So simply that's what we need to do. So if you do that, then this one is same as this way. This one. That's the closed form solution of this one. Same way. This is the closed form solution of this one. Okay? Yeah.
It's like the first equation, first line is alpha left side, but right side the alpha is very modulation.
Yeah, right. I think that's typo, right? The alpha is just constant. So there should be alpha here. Yeah, right. So there should be alpha. Alpha is missing here, right? All the others. Yeah, alpha is just constant, so you can bring it out. So alpha should be somewhere here as a constant, right? So that's a typo. So this Q function, including beta, this Q function is replaced to this integral equation. Okay, right? So alpha is something else, so that's missing.
Downside is
Here?
Rayleigh fading and Nakagami fading channel is the same as flow with the MDF.
That's right. That's another mistake, right? Yeah, right. So this one, that's correct. But this one, since this is another pattern, right? This is the power to the m, so that should be something else. I think I just simply the copy and paste to this one, and I forgot to change this one. Yeah, sorry about that. I'll make it. I'll correct it. Okay, so that's wrong, right? That's something else. In fact, this one actually is a little bit more complicated. This one is another pattern, but this one is actually this term to the power m. In fact, this is not as simple as this. There is a summation here, another summation here. There is a binomial distribution. So that's a little bit difficult. Okay, so yeah. But what we need to do is that, what we have to remember is that whenever we find this kind of pattern, then we'll refer to the book. The book will tell you what exactly is the solution. Yeah, here are the patterns that I mentioned earlier. Okay, sometimes you find this pattern, this another pattern. We have so many patterns like this. Okay, so whenever you do performance analysis, especially the BER analysis, eventually you probably have to reach one of these patterns. Okay, whenever we reach one of these patterns, that's it. We're referring to the book that will give you solution. Yeah, here is the one, right? Here's the one that I just talked about. This is the pattern we just looked at for Nakagami. This one shows that the sine squared divided by sine squared plus c to the power m. Okay, this is the one that we just looked at, and this is the closed form. Okay, so depending on your solution, depending on your problem, c may be something. This c is another just parameter. Maybe you have your own c. Okay, put that one here, and then this is going to be your solution. And the reason that I didn't show you the closed form for each of these patterns is that it's very complex. Okay, we have no space for putting all the closed form, but remember that these are the another patterns that you may want to reach. Okay, and you can refer to the book for actual solution. And these are the example of BER in case of MRC. Okay, and this one, in fact, was one of the midterms question, right? Yeah. So we always start from this generic integral equation. This is the probability in case of AWGN. This is the probability. This is the PDF of your SNR. But in this case, the PDF of SNR is the PDF of MRC, because in this example, I use MRC. So therefore, I use the output SNR, PDF of output SNR of MRC, which is this one. And since we use a BPSK, this one, Q function of root square of 2 gamma, this one is a BPSK. So you just put that together and then try to solve it. And then you'll find this pattern eventually. Okay? Then this pattern has this closed form solution. This slide and the next slide basically shows you, what is the typical approach, what other people doing. So capacity, generally, when you look at the capacity analysis, okay, you have to think about two different cases. Okay, there are two different categories. First case is that channel state information is known only at the receiver. Okay, if this one is only available at the receiver, then what you need to do is that you have to do your best only at the receiver in order to increase the capacity, because transmitter is completely out of the picture, right? Because transmitter is not even involved. Transmitter has no knowledge. So if you look at all these techniques, these are all the techniques that you do in the receiver. Receiver design, MIMO equalization, right? What is a MIMO equalization? In MIMO, right, we have two receive antennas. So there is a co-interference, co-channel interference. So because of the co-channel interference, you need to have equalization. For example, like this one. Zero forcing, MMSC, maximum likelihood, successive interference cancellation. Each one has its own advantages and disadvantages. Typically, for example, right, a maximum likelihood, this is considered to be the optimal receiver, which means that performance is optimal, but this is so complex. Simpler version would be the minimum mean square error or zero forcing. This is even more simple, but you lose some performance, right? So there's always trade-off. Successive, but these three are linear receiver. Successive interference cancellation is nonlinear, is a nonlinear system. Typically, the nonlinear system gives you a better performance. The reason is that successive interference cancellation has a feedback loop. Inside the receiver, you have a feedback loop inside the receiver, right? That's why we say this is nonlinear, but that actually gives you better performance, but complexity is pretty high because we have the feedback. Okay, you do a loop. But anyway, there are a lot of people who are doing research on these things. There are so many outputs, so many research outcomes about these things. Okay? Another category is that when CSI, channel state information, is also known at the receiver, also known at the transmitter. Assumption here is that there is a feedback channel, and possibly the feedback channel is ideal. Okay? Assume that what we are interested in this case is that how to design the pre-coding matrix or pre-coder. What is pre-coder is that, as you see here, this is a pre-coder, which means that this is done in transmitter, right? Before transmitting, you do some pre-coding or pre-filtering or beamforming. Okay, all those three, words are pretty much the same thing. So how to design the pre-coding? That's definitely a interest for us. Okay, and when you do the pre-coding design, whenever you do something, right? Whenever you design something, there must be a goal. There must be, whenever you do optimization, there must be a goal. Typically, we can think about two different purpose of the optimization. First thing is maximizing capacity. Second is error rate. Okay, but when you choose any pre-coding, you have to first decide whatever you want to do. What's your goal? Based on that, you formulate your optimization problem, and then solve the optimization problem, which gives you a solution, which gives you a pre-coding design. That's how we can do. And the CSI is also known in the transmitter. Then you can also think about the power allocation, transmit power allocation, because transmit power is the one that you can now play with. Okay. And limited feedback, this is another type that, what if we have non-ideal feedback? That's about this one. And these are the diversity, okay? And we cover all these things, so let's skip that. Okay, today's topic is adaptive transmission, okay? So for adaptive transmission, we're first gonna define what that basically means. First of all, let's go to the basic and start to talk about simple model that we already know. So we have a transmitter, as you know, right? Originally, we have a bit stream. Let's say this is S. I is just the index. We have S, which is original information. It could be bit or it could be symbol, doesn't matter. X is what is actually transmitted through the transmit antenna. That's X. X is transmitter symbol. H is channel noise, and Y is what you receive through the receive antenna, and eventually you are going to recover the S hat. Okay, simple model. Now we're going to make a block diagram picture about this model. So here's what it is. Let's think about transmitter a little bit more detail. In the transmitter, you must have a modulation and coding. Okay, these two are generally separate. So you may have a modulator. You also have a channel encoder. Okay, those things are modulation and coding. And there may be, not always, but there may be a power controlling block. Okay, it can be. In the channel, we can model this channel as a black box like this. And you see that there's a channel fading, H, and noise. And you see that fading is multiplied and noise is added, right? Because noise is additive, fading is multiplication. So we can simply model this one as this way. In the receiver, since you have done the modulation and encoding, what you need to do is demodulation and decoding at the receiver, okay? You basically undo whatever it's done here. And in addition to that, whenever you receive Y, from this Y, what you need to do is a channel estimation. The reason of doing channel estimation is to estimate H. Okay? Estimation may not be perfect, so you probably get the H hat. Okay? Ideally, H hat should be same as H, but always estimation has an error, so you have H hat, which comes from channel estimation. And this H hat, estimated channel, is now feeding back to the transmitter. So what I'm saying here is that I'm assuming the CSI, channel state information, is available at the transmitter by doing this one, right? This is feedback channel. What is not considered here in this picture is the delay. In actual system, there is a delay, right? Even though you have I, index I, somewhere here, whenever you go through all this procedure at the receiver and feeding back, this feedback channel may have its own delay, right? Because we do all this processing. This is not instantaneous, right? You have some processing delay. So there may be like I minus some delay. But for this moment, let's ignore the delay. Okay? And then this is the picture, general picture. So it says adaptive modulation coding, so we're going to talk about that in a minute. Before that, right, we're going to generally talk about several different ways of dealing with the fading channel. First of all, in wireless channel in general, right, what we need to do is that we have to use the techniques against the fading channel, because fading channel is typically the one that, it gives you a bad performance, right? AW channel is pretty good, but whenever you have fading channel, you have a very bad performance, which means that the fading channel is the one that we have to fight against it. So there are several techniques against fading channels. The first one is that first technique is try to mitigate fading channel. You try to reduce the fading effect of the channel. That's the first approach. The reason of try to reduce the fading effect is to improve the error rate. Okay? Because whenever you have fading, sometimes you have a very, very bad error rate, right? So you want to reduce the fading, therefore you want to improve the error performance. Okay? There are several techniques of doing it. First one is the diversity combining system, right? We already talked about diversity. And this is the first reason. Why we want to use the diversity? Because we want to reduce the fading. That way we can improve the BER. Okay, that's the main reason. Another possible technique is to use the variable power allocation. That's what I'm going to cover in the next slide. So what that basically means is that if CSI is available, if the channel state is available at the transmitter, now the transmitter knows the channel, so therefore transmitter can now change the power depending on the fading channel, right? So I'm going to cover that next slide. Another possible category of dealing with the fading channel is that we can take advantage of the fading channel. Not mitigating, but taking advantage of. What that basically means is the first type is that we have a fading channel, right? And we want to reduce the fading effect. That's the first approach. Second approach is that we have a fading, but now we say, okay, that's fine. There's a fading. Okay, I'm not going to try to reduce it. That's fine, but I'm going to take advantage of it. Okay, I'll talk about that in the next slide. The possible approach is the variable rate allocation, and also you can use a rate and power. Okay, so let's cover one by one. First one, diversity combined systems. We already covered this one many times. So let's look at this picture. This is the setup, right? In order to use the diversity, the typical way is that we use, let's say, 2 antennas. That way we can achieve diversity order 2. And in this case, using MRC, for example. Here, the picture basically shows you that if you think about only green, okay, we have a lot of fading. We have 2 antennas. So the green is the signal from first signal to the first antenna. Blue one, blue broken one line curve is the receive fading channel to the second receive antenna. So if you think about only green or only blue, it has a lot of fading. So sometimes it goes down to here. You have a lot of fading, like sometimes the deep fading. But since you have 2 of them and you select the better one, right? Using the selection combining, now eventually what you get as an output is the red one. And as you can see here, the red one does not have a deep fading. Red one actually has a less fading compared to green or compared to blue, right? Right? The green one is like a more fluctuation, more range of fluctuation, but the red one is fluctuating only this range. So now what we can see is that by using this diversity scheme, combining scheme, now we are reducing the fading. What is important is that we want to avoid deep fading. That's the most important thing, because this is where your packet is broken. Okay, somewhere here it's okay, but here it's deep fading. All of your bits are completely gone. Okay, so this is what we want to avoid, and by doing this, by using multiple antennas and applying the diversity combining schemes, we can avoid, probabilistically, we can avoid deep fading and try to reduce the fading, okay? So that's the main reason. That's how to deal with, how to mitigate fading channel. And by doing that, you see the performance, right? The BR performance, like this. Another way to mitigate fading channel is the power allocation. So now, going back to our previous model, here, let's think about the power control block right here in the transmitter. So at the receiver, after you do channel estimation, now you estimated H hat, which is estimated value of fading, and then feeding back to the transmitter. Now the transmitter knows that how the H moves, like this, right? This is H. In fact, this is H squared, but anyway, let's say, just think about this as H, okay? H goes up and down. This is a fading profile. Then once the transmitter knows its own H, its own instantaneous H, then what this guy can do is that this guy can allocate the power in an inverse way, right? Inverse way. So this red one basically shows you the amount of power that's allocated by transmitter. So when you have when the channel is under deep fading, now this guy increase the power, allocate large amount of power at that instant. Okay, if the channel fading is pretty good, then this can allocate just some amount of power. That way, what happens is that since the channel is, for example, like this case, right? Channel is very weak, but you are transmitting very strong power. That way, so somehow you cancel out. Therefore, from the receiver perspective, your SNR, received SNR, is going to be, ideally speaking, constant, right? Ideally speaking, your received SNR is constant. That's a channel inversion, because this one, H, power allocation, this one is kind of inverse function. So they just cancel out somehow. Therefore, your receive SNR is constant. If you want to make your receive SNR to be constant, then what happens is your bit error rate, look at this bit error rate right here, right? Bit error rate always is a function of SNR. But as I said earlier, this P of X, which is transmitted power, is inverse of H. So therefore, these two are cancel out somehow, right? Because these are inverse function. So this is always constant. Therefore, your bit error rate is always constant. That means it's good sign. Why is it good? Because this is where everything is broken, right? At least we avoid this one, and our bit error rate somehow is constant with this level. So that is actually a pretty good way, but there is problem about this thing, practically speaking. First reason, this is not instantaneous, okay? You already have some channel, you already go through this channel, and by the time you're feeding back this information, this time is already gone, okay? So always your power allocation is outdated or somehow after some delay. So you are not expecting truly inversion, right? That's one problem. Another problem, maybe bigger problem, is that since we are talking about channel inversion, what if you have a very, very deep fading? In that case, your power has to be very high. Simply, that's not possible, okay? You are not having that amount of, you don't have that amount of power budget, okay? But even though you have a power budget, that is really not preferable, and that is not possible by the system, because typically in transmitter, in typically actual system, you have a power amplifier, you know, in circuit wise, right? You have a power amplifier, there's some circuit here, and that power amplifier has a certain linear region, and blah, blah, so you actually cannot do that, okay? Your transmitter cannot be infinite. So if you really want to apply these things, right, what we need to do is that we have to use some truncated channel inversion, which means that we are trying to make a channel inversion as much as we can, but the power has to be truncated at some point, okay? Maximum power cannot exceed some value. That's a truncated channel inversion. That's one way you can apply if you really want to try. But I don't see many systems using this technique. In fact, none, okay? Just in the book, in theory, this is possible, but not really practical. Okay? But that's another possible way to mitigate the channel fading. Now let's think about different approach. Okay? Previous two approach, diversity technique and power allocation, variable power allocation. These two techniques are trying to reduce the fading. That way, you are trying to improve the bit error rate. Now let's think about a little bit different way. Here, in the variable rate allocation, still you want to have a feedback. Okay? Our estimated fading still has to go back to the transmitter. Now, in this transmitter, we don't have a power control block, which means that I'm not gonna, I'm not gonna use the power control. Okay? My power, transmit power is constant. Okay? Let's assume that we transmit constant power. Okay? But what we are changing, power is constant, but what we are trying to modify or changing, depending on the channel, is the modulation and coding. So that's why it says adaptive modulation and coding. Earlier, in the previous picture here, right, power allocation, our modulation coding is constant. We use BPSK, we use convolutional code, okay, for example, right? If you set it that way, you always use that. Modulation coding is fixed, okay? But you change the power. But in this case, your power is fixed, but you are going to change the modulation coding depending on H. Okay, that's the variable rate. Okay, now let's look at this picture. This green one is again the same fading profile. Okay, we already looked at this fading. Okay, and earlier we are trying to reduce the fading, and that's what we do. But here in this case, we are not trying to reduce it. The fading is the same as what we have. But instead of reducing the fading, what we can do is that look at this region. Here is the mode TX, mode 1, 2, 3. So meaning that it's a modulation 1, modulation 2, modulation 3. This is no transmission, that means. So what that means is, based on this fading, H, okay, instantaneous H, sometimes, for example here, right, sometimes here, if you think that my current status of H is here somewhere, then my fading, my channel is a little bit bad in a certain region, so I'm going to use this modulation. Okay? But as time goes, right, my channel condition is a little bit improved. Now it's a little bit better. In that case, I'm going to use a little bit higher modulation. Okay? But sometimes you go that way and you go back to the little bit lower modulation. Eventually, sometimes you go even further down, right? You are on the deep fading. In that case, you may want to decide, okay, this is too bad. My channel is too bad. So anyway, if I transmit something anyway, it'll be broken anyway. So let's not transmit. Okay? So that kind of decision, you're trying to modify, you're trying to change the modulation coding depending on the instantaneous channel condition. That's the adaptive modulation coding. That's the variable rate. Why do we say variable rate? Because each modulation has a different rate, right? For example, this is BPSK, 1 bit per symbol. QPSK, 2 bits per symbol. 16 QAM, 4 bits per symbol, right? So you change it, okay? Based on instantaneous condition, channel condition. That's the motivation of doing this. And the last thing is that you can actually do this one at the same time. You can use power control. At the same time, you can also use adaptive modulation coding. Okay, in that way, this is just possible scenario. The red one is your power allocation. Okay, this red curve is power allocation, transmit power. And you also see that there are several different levels of modulation, right? So you can actually apply both things at the same time. Okay? Okay. Now, among these 4 techniques, diversity combining technique, we already covered that. And this transmit, the variable power allocation, this is pretty straightforward to understand, right? So there are not much things to talk about. So this is pretty straightforward. But this one, the variable rate allocation, this is the one that we want to investigate a little bit further, okay? Rate adaptation. Okay, so let's look at it a little bit more. As you see here, rate adaptation is try to adapt the modulation level depending on your varying SNR. So whenever you look at this channel, depending on the instantaneous SNR, you apply some modulation level for that instant time. Okay. Now the question is, then how do you decide and which modulation level is used for particular channel condition, right? And what modulation is used? There are so many different types. The PSK and the maybe 4 PSK, 8 PSK. There are PSK type, PAM, QAM. There are so many different types of modulation. Okay, so which modulation you want to use? That's one question that you have to answer. And typically for this adaptive modulation, we typically think about Emory QAM modulation. That's the most common one. Emory QAM modulation is like a QPSK, 16 QAM, 64 QAM, and those things. Those things are QAM modulations, right? So these are popular modulations to be used as adaptive modulation. And now, let's say I want to use these 3 modulations. In other words, I want to have 3 levels. Then, how do you select each modulation level? In other words, what is this threshold? You have to decide the threshold, right? That way, now you want to switch from one to another. So that has to be decided. Okay, how to select the modulation level. And last thing is that the SNR range and all those things. So let's look at that a little bit more detail. This modulation table basically shows you an example, how to decide. Okay, this one just shows you numbers. But from this table, we can get a little bit of idea. So first thing is that you see here phi, right? It shows that it's phi QAM. In the previous slide, I said M QAM, but this is M, basically same thing. This is the modulation order. 4 means QPSK, 8 QAM, 16 QAM, 32, 64 QAM, something like that, right? This is the QAM modulation, which means that this case is where you transmit 2 bits per symbol, 3 bits per symbol, 4 bits, 5 bits per symbol, okay? You're trying to increase the order. In other words, increasing the rate, okay? And what we also have to decide is the target bit error rate. This is a target bit error rate, 10 to the minus 2, or minus 3, minus 4. So first, another thing is that you have to decide what is your target bit error rate. That's another thing you have to decide. Okay, depending on your decision on the target bit error rate, these are the thresholds for 10 to the minus 2. These are the threshold for 10 to the minus 3. The unit here is the dB. Okay, these are the SNR, and each of these has the unit of dB. And if you have a target bit error rate of 10 to the minus 4, these are the thresholds. So now let's look at this picture, how to decide those values. Okay? First thing to do is that you have to plot the bit error rate for all these modulation. Okay? So in this case, right, here are the modulations. This blue curve is the BPSK. Okay? These are just Q function of root square 2 gamma, simply, right? This is the bit error rate of BPSK over 8WGN, waterfall curve, right? And when you use a QPSK, this is the QPSK, symbol error rate. And 8 QAM, the green one. 16 QAM, blue, the purple, right? Light blue, 32, and black one, 64 QAM. You know that whenever you increase the modulation order, your bit error rate is going to be worse, right? Generally? Is it true? When you increase the modulation order, your symbol error rate is generally increased. Okay? Your bit error rate is also increased somehow. But remember that we discussed the symbol error rate and bit error rate several weeks ago, right? This picture is a symbol error rate. Okay? Not bit error rate. Why is that? Yeah, that's an interpretation from this picture. You know, when we have this picture, yeah, that's true. If we have a BER, bit error rate, right? Then this blue curve, BPSK, this red curve, QPSK, must have been same. Okay, these two should be same. But my question actually is that why do we have to use symbol error rate, not bit error rate? That's my question.
Because we are on the channel, not at the end. After that, we are getting bit error rate. So that is on the interface, you can say air interface. In the channel, we are estimating the channel at this point.
Yeah. Right. So our interest is the channel, right? No matter which one you use, okay? Regardless which modulation you use, we're going to transmit one symbol anyway, right? Okay? We're going to use one symbol by symbol transmission. We have one symbol, but sometimes if channel is good condition, we're going to contain more bits on that container, okay? Symbol is just one container. We are not changing the size of the symbol, right? If the channel condition is good, we have more bits in there. Channel condition is bad, we may have 1 bit. Okay? So we always have to think about symbol error rate, So from the symbol error rate perspective, now we have a BER, the symbol error rate for BPSK here, QPSK here. As you have higher modulation, your BER, your symbol error rate goes further to the right. Okay? So you plot all these things together like this one. Now, we also talked about the target bit error rate, right? So as an example, let's say our target bit error rate is 10 to the minus 2. Just an example, okay? In that case, now let's try to follow these graphs. Initially, when you have SNR 0, we start from here, the lowest modulation, and then go along this curve, right? Until that your next modulation is satisfied this target bit error rate. Your QPSK goes down, and at this point, your QPSK satisfy your target bit error rate, right? So at that point, now you switch. Even though you switch, your QPSK still meets your needs, okay? Still your 10 to the minus 2. If you switch right here, right, then your QPSK provides you a higher bit error rate, so your target bit error is not satisfied. You see what I'm saying? So by this time now you switch, okay? Because you can go even further, right? Then you can probably get to 10 to the minus 4 and 5, but that's not necessary, okay? Because our target bit error rate is 10 to the minus 2. As long as our target bit error rate is 10 to the minus 2, I'm good, okay? So this is the threshold that now you can switch. By switching, now you use QPSK instead of BPSK, so you can transmit 2 bits instead of 1, right? So now you switch. Same way, you keep using it as SNR is going high, going large, you go down here, right? And this is the time now you can switch to the next modulation, because next modulation now meets the 10 to the minus 2. That way, so you can switch it that way. So this red curve basically shows you how you switch from one modulation to another. And each of these value, right? Each of these value are the thresholds. These values are thresholds. So if you go back to this table and look at the 10 to the minus 2, these values, right? These values are this value. Okay, each of these value are the threshold value you found in the table. Okay? And if you want, then you can have even higher modulation. I have only up to 64 QAM, but if you want, and you can have even 128, 256 QAM, then there's another jump at there, right? Okay, that's how you decide the thresholds. So as you can see here, if your SNR, instantaneous SNR, if your basically SNR changes, right? We're thinking about instantaneous SNR. If your instantaneous SNR is within this region, then which one do you use? You use BPSK, because BPSK satisfies your bit error rate. Now let's say your instantaneous SNR is pretty good. So now you're in this region. Your instantaneous SNR, for example, is like 17. In that case, you can use this modulation, which is 16 QAM. Okay, that's how you do it. So as the channel varying, now sometimes you use this modulation, that modulation, like this, depending on your fluctuation. Okay, that's how you changing the modulation level. What can happen is your channel condition is very bad. You're deep fading. Your channel condition is very bad. So your channel condition is somewhere here, like maybe 1 dB or something. In that case, you have two choices. First choice is that since the channel condition is very bad, you're probably trying to use the lowest modulation possible. That's a BPSK. But even with BPSK, your target SNR is not satisfied. Okay? But that's the lowest thing anyway, so we just use it. That's one option, because that's the lowest thing possible, so there's no other option. If you want to use something, then that's the one, right? So that's one option. Or another option is that even though this lowest modulation does not satisfy my target, so I'm not going to transmit. That's another option, second option. Okay? So in this case, it's up to you. Some people say no transmission is useful sometimes because anyway this is not satisfied. But some other people say, okay, maybe transmitting, even though that's garbage, transmitting something is less than nothing. So just transmit something. So it's up to you, okay? But that's how you find the threshold, and that's the how to operate. If you use the target bit error rate of 10 to the minus 3, okay, then how do you do it? You have to use bit error rate all the way until the QPSK goes to that way, right? So this is where you jump to the next one. Same way, this guy goes to 10 to the minus 3 right here, right? So you have to go all the way to here, and then you switch, like this, okay? That's how we decide the thresholds. Now, in the previous slide, right, previous picture, we said adaptive modulation. We are basically changing the modulation depending on your instantaneous channel condition. But now we can also think about is that adaptive coding. You can do the similar thing with the coding, okay? There are so many different codings. What codings can you have? There are so many of them, right? Here are some examples which are provided in MATLAB. I use these things because MATLAB provides these things, but there are many, many different codings. The most popular coding technique is a convolutional coding and turbo coding these days. If you think about like a 3GPP LTE, the recent wireless standard, they use a turbo coding, okay? But turbo coding actually is pretty complex, so the MATLAB does not have turbo coding inside the MATLAB. It's not a built-in function. So anyway, so that's why I was not able to plot it here. But each coding has its own gain, right? So let's look at here. Earlier, by the way, in the previous picture here, adaptive modulation picture, right? I assumed that no coding, okay? In this case, coding is not there. I only changed the modulation. All these things, no coding. In this case, let's think about the coding. The blue one is no coding, like blue one, right? And if you use Hamming code, simple code, right? This is very simple block code. When you have Hamming code, because we use the coding, there's a little bit of coding gain. You see that the red one is a little bit moved to the left, right? That's the coding gain, but that's not that big. Another coding called GOLA has a little bit more gain, and convolutional coding has a little bit further gain. Convolutional coding can be used with the two different information bits. It's called hard information or hard decision, and another thing is a soft decision. To understand this one, we have to go into a little bit detail, but simply speaking, this is how things work. In convolutional coding, what happens is this is not a block coding. These are the block coding, but this is not block coding. This is called a cyclic coding. So how to do that is that this case, right? This is like a block coding, which means that you take the block of bits and do an encoding and transmit. And on the receive side, you receive a block, which goes to the decoder, and again, you get a block back, right? In convolutional coding, that's not the case. It's cyclic, which means that you have a series of bits, just series, infinitely, okay? And then those series of bits are coming to the encoder, and as the next bit's coming, your output is coming out, right? And those outputs, serial outputs, and also serial inputs, right? Those serial outputs from the encoder is transmitted, and the receiver, you receive the series of bits, and those things goes into the decoder, and again, your output is a series of bits, okay? It's not a block by block. It's a series of the block. So which means that your information, let's say 1-bit information is affecting all the other bits afterwards. If you do the block coding, right, only the information in the block will affect the other information in the block. Okay, block does not affect another block, right? Block by block, each block is independent. But here it's not the case. There's a lot of correlation between the bits because there's no concept of block. When you do that, right, one bit information is affecting, has influence onto another bits. So therefore, when you make a hard decision means that you make a decision of either 0 or 1. Because eventually, what we want to decide is the bits, like 0 or 1, right? That's eventually what we have to decide for each of these bits. Because originally it was bit 0, 1. So after you do all this processing, eventually you have to decide either this 0 or 1. But that's hard decision. But inside here in the decoder, when you do the iteration, okay, while you're doing iteration, you can do a hard decision for each bit. And then those hard decision is now having influence to all the following bits. So how to make a decision, temporary decision, that's important. And you can use a hard decision or soft decision. Hard decision is like a 0 or 1. Even there is a temporary decision, you make a 0 or 1 decision. That's hard decision. And that decision is now influenced to the rest of the bits. Soft decision basically says that you are not going to make a temporary decision like a 0 or 1. You make a decision like it's likely 0, it's likely to 1, or something like that. There are several steps. Typically, we use 8 different steps. Okay? 8 different steps from means that 0 to 7, right? That's a soft decision. If the soft decision of 0 means it's definitely a hard information 0. Soft decision 7 basically means that it's definitely close to the hard decision 1. Okay? That's what it looks like. Okay? So as you have higher value in the soft decision, you have more likely to be hard decision 1. Something like this. Okay? That's a soft decision. And if you make a soft decision, okay, then those soft decision, that's a temporary decision, right? Those soft decision will now influence the rest of them. Okay? So that's actually a better performance, much better. Okay? Detail of these things, maybe we can cover then, maybe we have time later. So depending on when you have a hard decision or soft decision, you have a different performance. Here the purple one here, right? That's the convolutional code with the hard decision. Even with this one, now you see the pretty high gain compared to no coding, right? There's a big coding gain. But when you have a soft decision, now look at the light blue. It's right here. So it has really big gain. Okay? From here to here is a lot of gain. Now let's think about the turbo coding. It's not in here, but if you use a turbo coding, right? Then turbo coding is somewhere here. It's even further here. That's where your turbo coding is. So that's why the turbo coding, somewhere here, turbo coding is very, very fantastic. It actually, it is the best code known so far. Okay? But it's complex a little bit. But complexity can be dealt with, right? We can always make a faster chip. We can make a hardware and things like that. The complexity may not be a problem at some point. Initially, that was a big problem. People think that turbo code is so complex, so it cannot be implemented. But as the technology advances, right, all this complexity, problem is not a big problem at some point. So complexity is not a big deal. Therefore, typically these days, for example, in the LTE, we use a turbo coding. Okay? So that's right here, something here. So if you think about turbo coding, we have really big gain. It's not like a 10 dB, it's a lot of gain. Okay, so that's the coding. So now from this picture, what you can see is that depending on which code you use, you have a different gain. In that case, right, maybe we can think about the similar thing. Within a certain range of SNR, we can use one coding. If you have another range of SNR, you may want to use another coding, right? That's a possible way. But in that case, you may have to have all these different decoders. You have to have hardware for timing, you have the hardware for convolutional coding, turbo coding. You have to have all of those decoders, which is not easy to do it. That's why in a typical system, what you have is that you fix the coding type, for example, convolutional coding, or for example, turbo coding. You fix it. So hardware is we only have a turbo encoder, decoder, or convolutional decoder. But within that, you can actually change the parameter. Okay? For example, here, right? Even with the block coding, what could be the parameter for block coding?
Memory block.
Block size. Yeah, block size. If you have a large block size, typically you can expect a little bit more gain. Okay? So there's always a parameter for each of them. Convolutional coding, what could be the parameter? The depth. Okay? Inside here we have iteration, but when you do the iteration, it is like a filter. We have many filter tabs. So how many tabs you have, that could be a parameter. Turbo coding. There are several other parameters. In addition to, in fact, the turbo coding is not easy to understand, but turbo coding is, simply speaking, turbo coding is nothing but a several convolutional coding in parallel. That's a turbo coding. You have a convolutional coding here, another convolutional coder here. If you want, you can have multiple of them, but all these things are parallel. But if you just do a parallel, then all these encoder are making the same outputs, right? That's why when you're feeding the information, on the first encoder, convolutional encoder, you feed the information as it is. When you go to the second encoder, we do a randomization of the information. Okay, then the randomized input sequence are going to the second convolutional coder. That's how the turbo coder looks like. So turbo coder, inherently, that's the multiple of convolutional coder. Okay, so which means that turbo coder also has multiple parameters. How to design the randomization block, and how to set the tabs for each encoder, convolutional encoder, and those things. So depending on the changing of those things, you can have different gain. So that's how people do. For example, right? Let's say I want to use convolutional coding. In that case, I have a hardware for convolutional coding, and I play with all different value. Let's say I want to have a depth of 3 and play, okay, and measure the bit error rate. Maybe it goes like this. And I change the parameter. Now I want to use the depth of 5. And then again, measure the bit error rate. It goes a little bit further here. And again, change the parameter to 7, like this, right? So you change the parameter, then you draw all this bit error rate, and then you can think about the range of SNR, and you know, same way. That's how people do. That's how you do adaptive coding. This picture basically shows you an idea. You know, whenever you change a different coding, you get the different BER, so therefore you can think about the range of SNR for each of this as the coding. Okay, this picture basically shows you an idea. Okay, I'm not trying to say that we want to switch to different coding, completely different coding. That's not practical. You see my message? Yeah. So you typically in the practical system, you fix the coding type, convolutional coding or turbo coding. Okay, you fix the one type, and what you want to change is the parameter, okay, of that encoder, decoder. Okay, by changing the parameter, you get a completely different bit error rate. Okay, by doing that, you draw the multiple of them. Okay, and now you can find out the SNR range. Now, what typically people do when you design the system is that they put those two together. It's called adaptive modulation and coding. Some people call that as AMC, but more popular term is MCS, modulation and coding scheme, MCS. Okay, if you Google MCS, you'll find a lot of things, and all of the typical commercial systems, wireless standards, they use terminology MCS, okay, modulation and coding. In the modulation coding, what they're trying to do is that they are trying to change both of them. They're trying to change modulation as well as coding, depending on your SNR. Okay, those two are not independent. Those are the same. Basically, we consider both together. Okay? So adaptively change both modulation and coding. Okay? Depending on your SNR, instantaneous SNR. So generally, you use high modulation and coding scheme when you have good channel condition, favorable channel condition. You have a low modulation and coding with the bad channel condition, right? Then we have so many different modulation, like in QAM type, we have QPSK, 16 QAM, 32 QAM, 64 QAM. There are so many of them, and even in the coding, we have so many different way. So how to make a combination? That's the question. What would be a good combination, and how can you make it? That's one thing that you have to study. Okay, and another thing is that when you make a combination with a certain modulation with a certain coding, right? And you change another modulation and coding, you make a combination, so many of them, then you have to guarantee that each of the modulation can be distinguished. For example, right? Use one modulation and one coding, which gives you this BER, and you change the modulation and change the coding, both of them are changed, and you measure the BER, it looks like almost the same. Then there's no meaning, right? So what that means is when you choose a combination of modulation coding, you have to find it well so that these BER, at least the performance is kind of different. That way we can have enough SNR range for each of those combinations. So that's what we have to think about. And another thing to decide is that we can think about so many combinations. So how many MCSs, how many combinations do you need? Okay? Or how many combinations are necessary? That also has to be decided. But that cannot be random. That has to be decided based on some other factor. For example, feedback. Here, feedback message, right? Why is this related to feedback message? Because in order to do this modulation coding, we need a feedback, right? We have to feedback the channel condition. That way we change it, right? So somehow the feedback message is related here, but typical system, in practical systems, feedback message can never contain your H hat. H hat is your actual estimated channel gain, which is going to be a complex value. That cannot be transmitted, right? In the practical system, what is actually transmitted is just bits. Typically just 2 bits or 3 bits, something like that. Even 3 bits is really large. Okay? 1 bits, 2 bits, something like that. It's a number of bits. So from those number of bits, a few number of bits, now you have to match between the feedback message with the proper MCSs. Okay? That's how we have to do, so we cannot make infinite number of combinations. Okay? But eventually, what the transmitter and receiver does is that they study all these things. They try to find what combinations are good, what combination of modulation codings are good, and also they have to study what would be the SNR range for each combination, okay? And they have to make it table, lookup table, okay? They have to make a lookup table that way so that later when you do actual operation, this is when you make an operation, actual operation, now you can look up the table. You don't have to calculate in real time. Okay? You don't want to do that. You want to look up, just a lookup table, and find out what will be the good modulation and coding scheme, and just use it, depending on your SNR. So this picture basically shows you an actual example that is used in 3GPP LTE. This is a recent system, so probably it's useful to look at what actually they do in the practical system, the recent system. It's a little bit hard to see here. But this one is MCS number, modulation encoding number. So in this LTE, we have 32 different MCS are defined. Second type, second column, says CQI, channel quality information. That's a feedback information. Okay, that's a feedback message. Okay, the receiver basically feeding back the channel quality information to the transmitter. So this is feedback. Here are the modulation: QPSK, 16 QAM, 64 QAM. Okay, they use only 3 of them. Okay, they switch between these 3 different modulations. And the last thing here is a spectral efficiency. Spectral efficiency. Okay, what is a spectral efficiency, by the way? What is the definition of spectral efficiency? Simply speaking, spectral efficiency
Is to retain the shape of the signal.
shape.
It's a,
It's a little bit different, but spectral efficiency has the same unit as capacity. What was the unit of capacity? Bits per second per hertz, right? BPS per hertz. Spectral efficiency has the same unit, which means that spectral efficiency somehow has the same concept as capacity. So let's think about spectral efficiency. Now we have a spectrum. Okay, we have all the frequencies, we have spectrum. What would be the efficient way to use the spectrum? With the same amount of frequency, let's say 1 hertz, okay? Within 1 hertz, how many information you transmit, okay? You have a more transmission, large spectral efficiency, simply speaking, right? That's also same as a large capacity. So that's why it's the same thing. Spectral efficiency basically means that how many bits you transmit per hertz. That's a spectral efficiency. What is the best way to improve the spectral efficiency? So far, all the knowledge that we learned so far, best way is MIMO, right? MIMO, right? In MIMO, you basically extend into space dimension. Therefore, the spectral, you can use 1 hertz, right? But we increase the space domain, so you can increase the BPS. But these things, right? The adaptive modulation and these things help. So this spectral efficiency is actually has to be calculated, but this one is actually pretty fractional numbers. But as it goes, right, you see that the spectral efficiency is increased. One of the reasons is that you use higher modulation. Okay, if you increase the modulation, you can, simply speaking, you can increase the spectral efficiency, right? Using 1 hertz, you use higher modulation. Eventually, that means you transmit more bits. Okay, so best way to do it is increase the modulation. That way, as you see here, the spectral efficiency is increased. But now the question is, in QPSK, why not it's just 1? And in 16 QAM, why not it's just 2? Why not, in this case, it's just 4? The reason is that the coding is involved. When you have a coding, right? Channel coding in this case, right? Whenever you use channel coding, that's a little bit bad. That actually reduces your spectral efficiency, right? Why?
because you are stuffing more bits.
Yeah, you put more redundancies, right? You put more redundancy in channel coding. So therefore, your spectral efficiency becomes lower. But yeah, in that case, the advantage of doing that is you get a reliability. Okay, you get more protection. So somehow, higher modulation will increase the spectral efficiency, but coding is reducing. Okay, but anyway, and using MIMO is actually multiple of that. So put that all together, then you get a non-integer number of spectral efficiency. So as you see here, these are all QPSK, but they are using different coding rate. Okay, coding also has a coding rate. When you have a coding rate, higher coding rate, okay, that basically means that you have higher coding rate. Okay, let's think about channel coding a little bit here, because that's a word that you may use sometimes. Whenever you say channel coding, there's a coding rate. Let's say our coding rate is 1/3. Okay? Let's say we are using the 1/3 rate. What does that mean? Okay, coding rate cannot be higher than 1. Okay? Sometimes coding rate is 1/3. That basically means that you have original information like this. After you do encoding, now the after encoding, this size is going to be 3 times of original one. Okay? That's 1/3. So if you have higher coding rate, let's say it's close to 1. Okay? It's close to 1. That means you have, yeah, almost the same. Less redundancy, right? Almost close to the same. We have only small redundancy. That means higher coding rate. Small coding rate basically means that you have more redundancy. Okay? In this case, as you see here, it has a very low spectral efficiency, which means that we have more redundancies. Since you have more redundancies, you have a less spectral efficiency, right? Right? In this case, it means low coding rate. Okay? As it goes, you use higher coding rate. Okay? As it goes. That's how things work. Because in CQI, right, the channel quality information, let's look at the next slide here. This one is a channel quality information table defined in LTE. So you see that we have 16 different channel quality information, 0 to 15. And depending on which channel quality you have, this is a little bit low channel quality, very good channel quality. So depending on channel quality, they are suggesting to use these modulations. And these are coding rate. And how do they decide the channel quality information? These are the information that receiver has to feed back. So which means that we have 16 of them. So our feedback message is how many bits? 4 bits, right? Our feedback message is 4 bits in this case. Okay, that's only transmit. Okay, we are never transmitting H hat. We transmit this value. But what is already agreed upon between the transmit and receive is that when, let's say, when you feedback CQI 5, that basically means that this one corresponds to a certain SNR range. That's already decided. This one is our SNR range, pretty low range. This is a SNR range, pretty good SNR range, right? That is already decided. So by knowing CQI, you already know approximately, right? You already know that, what is your instantaneous SNR in terms of range, right? At least you know that. And once you know that, right? Once you know the CQI, that means here, since CQI 2, this means that we have a little bit low channel quality. So when you have a bad channel quality, we have to use more redundancy, right? Because it's bad channel quality, you have to have more redundancy, which means that you have to reduce the coding rate. Therefore, your spectral efficiency is lower. Okay, so in this case, you use low coding rate. Modulation is same. Modulation is QPSK, but you use a lower coding rate, so you put more redundancies. So spectral efficiency is low, but channel quality is bad anyway, so that's the best thing we can do. And as the channel condition goes higher, in this case, right, you have a very, very excellent channel quality, like 14, for example. So you use higher modulation. In addition to that, you can use some high coding as well. So your spectral efficiency is now increased even 5 point something, because both you use higher coding as well as you use higher modulation. Okay, both of them increase the spectral efficiency, so you use higher efficiency. Here you see that we have only 16 CQI, but we have 32 MCSs, right? So it's not one-to-one mapping all the time. We have a CQI 2. These two MCSs are mapped to CQI 2. For CQI 6, we have 3 different choices of MCSs. Difference between these 3 MCSs is that these 3 are mapped to same CQI 6, but these 3 are very interesting, because here we receive the CQI 6, which means that you have a same SNR somehow, right? But there are three choices you have. First two choices use a QPSK, but with a different spectral efficiency. Okay? But third type, you see that it uses 16 QAM, not QPSK, but 16 QAM, but you see the same coding rate. How does it happen? Hmm? Coding rate, yeah. Yeah, that's right. You basically trade off between modulation and coding. In this case, right, that's the last MCS for QPSK. So in this case, you probably have a very high coding rate. But in this case, that's the first one in the 16 QAM. This one uses 16 QAM, but this one uses a very low coding rate. So sometimes when you play with modulation, higher modulation with low coding, or low modulation with high coding, sometimes you see this kind of thing, okay? Sometimes you can make both of them to be same spectral efficiency. Okay? Sometimes this happens. So anyway, so these are the actual system parameter that are used in 3GPP LTE. Now let's think about another recent system. 802.11n. This is a wireless LAN. Okay? You guys probably use wireless LAN, and most of them probably it's 802.11g or N, right? N is popular these days. N is the extension of wireless LAN to the MIMO. So in N, we have a MIMO technique. So this is actual picture that is in the spec, and they actually have a lot of MCSs. Here in this table, I show you up to 31, but I think there are more. If you look at the spec, actual spec of 802.11n, I think there are 64 MCSs. Okay, but I show you only 32, the first 32. The second column shows you number of spatial streams. What does that mean? They use MIMO, right? This is the number of water pipes in our illustration, okay? Number of spatial streams, okay? Definitely, if you increase the number of streams, definitely you expect a higher throughput, right? These are throughput. Actually, these are throughput, right? All these are throughput. Okay? Generally, you expect a higher throughput compared to the one number of streams. And they also have adaptive modulation, and their adaptive modulation is like a BPSK, QPSK, 16 QAM, 64 QAM. They have 4 choices of modulation. And look at this one. They also have a coding rate. And if you think about this one, right? For example, BPSK has only one coding rate, but let's look at QPSK. In QPSK, we have 2 MCSs mapping QPSK, and within these 2 QPSK, we have 2 different coding rates. But the first one is half, the other one is a 3/4, which means that for this one, low MCSs, they use a lower coding rate, meaning more redundancy. This one has higher coding rate, meaning less redundancy, because in this case, this is a higher MCSs, which means that this is supposed to be used for a little bit better channel quality than this one, right? So that's how things work. You see that you see all those things, right? Look at the last one here in the in case of one special stream. So MCS7. In MCS7, you use a 64 QAM modulation, the highest modulation. And also look at the rate, 5/6. That's almost close to 1, right? So they have very little redundancy, and they have highest modulation use. Why do they do that? Because they think that this channel condition is very excellent, so using these things is still okay. And if you do that, right, then definitely they can increase the data rate. Even with one data stream, single antenna, right, you can even have 150 megabps or 72 megabps. That's very, very excellent. Okay? So depending on the channel condition, you play with the coding rate, play with the modulation. That's how things work. Here in this plot, I think I forgot this one, but this is the throughput, And 20 megahertz, 40 megahertz basically tells you what is your bandwidth. Okay? The spec allows you to choose your own bandwidth. You can use a 20 megahertz channel. You can use a 40 megahertz channel if you have. Okay? So definitely if you double the bandwidth, you can expect a double throughput, right? Simply speaking. And the difference between this one and this one is that the size of guard band, guard interval. You know the 802.11 and the previous LTE are based on OFDM. Okay, we're going to cover OFDM next week. OFDM has several system parameters. Okay, when you design the OFDM system, there are many things to consider, but one of them is called the guard interval. Okay, guard interval. In this case, look at this one. This one is a little bit, even with the same bandwidth of 20 megahertz, this one has a little bit lower throughput. This is a little bit higher throughput, which means that this one has a little bit large guard band, a little bit low guard band. Because guard band is, eventually guard band is a waste, right? But but that is necessary. You need to have that. So when they designed the system, okay, they prepared two different guard bands, okay? So therefore, you have two different columns. So some of those things we'll cover in next week. So these are all the data, the BPS, mega BPS, data rates. Okay, let's briefly look at in case of OFDM. So here's the OFDM picture, not the system picture, but this is a transfer function, frequency response of the OFDM system. Look at this one. This one is the x-axis is a frequency domain. Okay, each of these box, each of this beam is a subcarrier, and this curve that shows you the channel condition over the frequency domain. These are the frequency domain, and each frequency may have its own gain, right? So what I'm assuming here is a frequency selective somehow. What does that mean? If I have the channel condition flat, like this one, okay? Ideally speaking, right? If we assume that our channel condition over frequency is flat, that basically means what? That basically means our impulse response in time is impulse, which is very ideal case. That's never happened, right? Because we always have a multipath, okay? We always have a delay. So because of that, so how many multipaths you have and all those things in your channel condition, your frequency response of the channel fluctuates. For example, like this, okay? And we have a subcarrier. That way, subcarrier has to be designed, okay? That way, I'm saying that OFDM has a lot of parameters to design. But anyway, let's design it. Let's assume that the system has been designed already, like this way. So each of these is a subcarrier. Now, what you can see from this picture is that each subcarrier has a different channel condition. These two channels probably have a very excellent channel condition. For example, these red ones, okay? These red subcarriers, this frequency range has a very low channel quality. So depending on that, what we can do is that we can assign a high modulation for these subcarriers and very low modulation for these subcarriers. So each subcarrier is independent in OFDM. So each subcarrier, you can use a different modulation. Like within this range, one modulation, another range, another modulation, like this. Same way as we did before. Earlier, in the previous picture, when we talk about adaptive modulation, we thought about only the time variation of the channel. So as the time goes, you have a fading. So therefore, you are adapting, right, your modulation depending on your time instantaneous channel, right? But you can do the same thing for frequency. Okay, in OFDM, you basically use each subcarrier as your container, as a carrier. So therefore, each subcarrier is independent. You can use a different modulation for each subcarrier. That is the fundamental reason why the OFDM is so popular. Okay? Maybe some side story. Okay. Have you heard the ADSL? DSL technology, right? DSL, I think, was introduced maybe 10, 15, maybe 20, 15 years ago, right? Some time back. Before that, let's go back to 20, 25 years ago, maybe 20 years ago. Everyone was using a telephone modem. Okay? What was the BPS of telephone modem? Initially, it started from the maybe 2400, something like that, but eventually it also advanced. Technology advanced, but it eventually went to the 56K or something like that, right? Something like that, right? But physically, telephone wire, everyone think that telephone wire cannot exceed 64K, but you must have an overhead, a little bit of overhead, like header, things like that. That's why you are able to only achieve 56K. So that is truly maximum you can achieve through the wire, telephone wire. That's what people believed completely, which is actually somehow true. But what other people thought was, and one of the pioneer for that idea was the Stanford professor John Chaffee. Okay, that guy and another guy thought about the different idea. If you use a telephone wire, okay, what was the reason that 64K or this K is maximum? What was the reason? What was the problem of telephone wire? Why you cannot achieve more than this? Because there are a lot of multipath and a lot of kind of symbol interference in telephone wire. When you talk, right, your voice is affecting, it has a lot of delay, a lot of echoes. There are a lot of echoes in telephone wire. So therefore, you need to have a very, very excellent equalizers. Okay? Equalizers can never cancel out your echoes. It will reduce it. But there's a certain limit. Okay? There's a certain limit that you can reduce it. So the best you can do is that you can try to reduce it. You want to use multiple taps. Okay? More taps, typically better performance. So you make a very complex equalizers with a lot of taps, but still there's some remaining echoes, remaining interferences, which you can never remove. Okay? Because of those remain, this is kind of limitation that you cannot exceed. Okay, that's what people believe. Now those new guys, right? Those guys came to the new approach and think about that. Now, that's the time domain analysis, right? Symbol interferences is what happened in the time. Now I transmit one symbol, interferences happen from one symbol to the next one. Okay, that's the time-wise. Now let's think about the frequency domain. So what they do is that they apply the FFT to go to the frequency domain, okay, like this one. And then they're trying to load some information on the frequency domain. Now what they realized was that since you have multiple intersymbol interferences, that basically means that your channel condition is never flat. If it was flat, then your channel impulse response already have the impulse, which means no symbol interference. Since you already have multiple symbol interferences, that basically means that your channel transfer function is like a lot of fluctuation. So go to the frequency domain, and we design the subcarriers narrow enough, like this, and then load a different size of modulation, different information for each subcarrier, and transmit in the frequency domain. Okay? That is the fundamental idea of DSL. By doing that, simply changing the time domain to the frequency domain to transmit, and in addition to that, you want to use this adaptive modulation concept onto the frequency domain. By doing that, now you can increase the data rate even to the 20 megahertz, 100 megahertz, 100 megabps. Okay? In time domain approach, this was the maximum. Everyone believed that. But using the frequency domain, they were able to increase the data rate even to the tens of megabps using the same wire, the telephone wire, right? This is what he said, actually. What he said was that he actually said that, you know, I went to some, I think, conference or somewhere, and he talked about that some time back. He said that he went to the Bell Lab, and he described all these things. Actually, Bell Lab was at that time, Bell Lab was the place that all the brilliant guys are, you know, working there, right? So he went to the Bell Lab and do a presentation about this kind of concept. You can do the frequency domain. We can achieve like tens of megabps, and everyone laughed. And that's what he said. But you know, but that was actually true, and that was proved by the technology. Anyway, so that was the idea. In frequency domain, we make a fluctuation, and we design the subcarrier very well, and then we use a different number of bits in each subcarrier. So these here we have like a 2 bit, 3 bits, 2 bits, right? Here we transmit 4 bits and things like that. By doing that, we can transmit much more number of bits. Okay, so this adaptive modulation concept is not new. Okay, we are using this everywhere. These are example of the table. From the analysis perspective, we want to talk about how to do the spectral efficiency analysis. This is a simple equation that tells you how to do it. Spectral efficiency, L. L is the number of subcarriers. We have a subcarriers, right? What it does is that K is the number of modulation you use. This case, I ignore the coding. Okay, I only consider the modulation. And K is the number of total modulations, modulation levels. And R of J here, right? That's the rate. Simply speaking, right, if you use QPSK, the rate is going to be 2. And 64 QAM, it's going to be 6. Okay, the rate is as simple as like number of bits per transmit. And P is the probability for each of them. How do you calculate this? Going back to this picture, let's say, from this study, now we find out this threshold, right? SNR threshold. Once you know this SNR threshold, now you can calculate what will be the probability that your fading profile falls into this SNR range. Okay, your channel basically changes over time. Okay, statistics of your channel maybe is Rayleigh. Okay, and you can simply find out what is the probability that your instantaneous channel quality falls into this range, SNR range. That's simple, right? Simple, right? If you do integration from 0 to SNR from 0 to infinite, okay, if you do integration of PDF from 0 to infinite, that's going to be 1, right? If you do integration from 0 to this value, okay, then the probability that your SNR goes into this range. You do integration from this value to this value. That's the simply probability of your SNR falls into this range, right? So it's very easy to do it. That's the probability of this one. So what that basically means is this is the rate that you use. That's the probability that you use for that modulation. Okay? And you calculate these things for each of these modulation level, each of those levels, and then you do a summation. Then that's going to be spectral efficiency. Simply, right? For example, these are the tables, and when you define the SNR, when you define the fading profile, right? It's the Rayleigh fading. Rayleigh channel has only one parameter, gamma bar. Okay, so you define a gamma bar of your own. Then now you know this one. Now you have a complete picture of your fading profile. Okay, your Rayleigh fading, and then using this table, now you can calculate the probability. You can also consider the modulation levels. Then you can calculate this one. As an example, if you do that within this table, you can get these things. What that basically means is that This is a 3 times L, right? So L is the number of subcarriers. So generally, average sense, you have a spectral efficiency of 3 per subcarrier. Okay, that's what that means. Which means that some subcarrier you have 4 bits, some subcarrier you have 1 bit, but in average sense, you have 3 bits per average sense, 3 bits per subcarrier. That's kind of what you can get with this example. Because in this example, I have average SNR to the 15, pretty good channel condition, right? But if you change this one, like some low value, then of course you have a low spectral efficiency. So it is a function of that. Way we want to cancel out. Otherwise, we can never decode it. I mean, this is a simplified picture. You do estimation, and this estimated channel goes into the part of that, right? And then you do all these things. So definitely you need to have that. Yeah.
About this project progress report, what should we rate on this? Like what we have studied until now, or do you want any simulation?
It'll be very good if you can have a simulation, but I'm not expecting a very detailed simulation at this point. But I want you to have some progress. That's all. Okay.
What should be the format?
Even for proposal, I didn't specify the format, but let's think about the format. Typically, think about the conference paper, right? As I said, our eventual outcome is going to be conference paper. When you look at the conference paper, right, you have a title, of course, you have an author name, you have abstract, and information, the introduction. Since this is a progress report, let's say proposed system, and you may have a performance analysis or simulation performance and conclusion and reference. These are the format of complete picture, right? Eventually in the final report, you probably want to have this format, okay, if you can. Now, since this is a status report, I'm not expecting conclusion yet, right? I'm not expecting the performance result. If you have a simulation, then that can go into the performance section, which is good, okay? Which is good if you can, but I'm not expecting that one at this point. What I'm expecting is that I want to have, even though that's not complete version, I want to have some of your introduction and also some brief summary, and then some part of a proposal, some part of a proposed system, or some part of your progress. So you can have some progress for the title of your section, or you can name as a proposed system, or this is the main part that you want to include. Okay? If you propose some system, then you want to describe about the proposed system. If you do a survey, right, then you want to describe about the survey, some of the ideas about the paper that you read, something like that. Okay? So this is going to be the main section. Earlier in the proposal, right, instead of this one, you may have some proposed system, or some proposed system, or some brief description. But in addition to this, this is the part of the section you may have in the status report. And now later in the final report, you want to make this section complete. In addition to that, you may want to introduce some performance section with the conclusion. Does it help? Yeah. Any other question? Okay, see you next week.